Okay, so we've done one example of a chi-square test, so now we're going to do another. So with chi-square test, we know the null hypothesis, H0, the assumption, is always that there is no relationship between your two variables, whatever they are. While your alternative, the thing you want to test, is that there is a relationship. You're not saying what it is, but you're saying there's a relationship. And if we do conclude HA is true, then we can say what the relationship appears to be. And just like any other hypothesis test, if the p-value is small enough, if the p-value is below our threshold, or alpha, less than or equal to alpha, we can say HA is true. But if the p-value is bigger than our threshold at alpha, then we've got no conclusion. We can't say there's a relationship, we can't say there's not a relationship. And the thing is with the chi-square test, our p-value form now changes. Right? It's no longer normal. We have to use the chi-square distribution. So we have to find this chi-star, which is like our Z1, using observed and expected values. Once we found that, we can put that into our p-value formula and look it up in the chi-square table. And in the chi-square, we need degrees of freedom, just like we needed with a t. So let's go ahead and do another example. So get this all the way up here. There we go. So this example says a professor wants to test whether there's a relationship between how well a student does on a test. So that's one variable, right? How well a student does on a test, that's one variable. And the number of beers drunk before taking the test. So those are two variables. The professor gives some students free beer, woohoo! Others get no beer. All the students then given the test. Below the results, conduct the appropriate test using alpha 0.05. So our two variables are, did they pass the test? And number of beers drunk. And notice here we kept it simple. All we have is two categories for each. So number of beers drunk is either 0 or not 0, right? One or more. And the pass the test is either yes or no. Okay, so here is our table. I'm going to do some lines here because we need to add, as we know, our totals, right? We need to add row and column totals, and we need to add overall total, then we need to find the expected values. So here we're going to have our row totals. Here we're going to have our column totals. And here we're going to have our overall total. Okay, so here we're going to take what? 26, this 26 here plus that 22. Oop, I'll change that. I was trying to do the plus without my lines disappearing. It's going to do so it's going to start doing though. Come on. Plus, there we go, 22. So that's 48. So there are 48 who passed the test, right? That's what the yes is here. So that's how I got that. So down here, I'm going to take 22 plus 30. Come on. That gives me 52. So there are 52 who didn't pass the test. Must have been a hard test. So overall, we know to get the overall total, I can just add those two row totals together. So if I take 48 plus 52, I get 100. So our overall total is 100. We're not told that in the problem, but we can find it by summing up the row totals. And we can do the same thing with the column totals, right? So here, for those who had 0 beers, there are 26 and there's 22. So I take 26 plus 22, which actually we've already done. We've got some symmetry going on here. So there are 48 who didn't get any beer. Take 22 plus 30. So there are 52 who had beer. And a quick check, if I add up those two, the column totals, well, it's the same as the row totals in this case. It's pretty silly, right? But we can, that's one way to check. The row and column totals must sum to the same overall total. And here, obviously, they do because they're the same values. So yeah. So our overall total is 100. So now we've got the observed values, right? That's at 26, 22, 22, and 30. Now we need to get the observed values, right? If I want the the expected values. If I want the expected values, we know what we do is we take the row total times the column total divided by the overall total, right? So that means in here, where we saw 26, I expected, well, its row is the first one, so that's 48. Its column is the first, that's also 48. And the overall total is 100. So here it's 48 times 48 divided by 100, right? So let's do that. So 48 squared divided by 100 is 23.04. So that's what I expected. Remember, the expected values are what you expect to see if there's no relationship, if H0 is true. So I saw 26, I would expect about 23. Remember, now look here, this is a simple example with only a 2 by 2 table. So actually, once I find that first value, the rest I could find by subtraction, right? Because they must sum to the same totals. So this one here, I could do it several ways. I could take its row total 52 times its column total 48 divide by 100. Come on, there we go. Or I could just take the either one. Okay, well, it's got symmetry here, but with this one here, I could take this column total 48 minus the value I got earlier, the 23.04, since they must sum to the same totals. Okay, so if we do that, we get 24.96. So 24.96. Obviously, by symmetry here, this is going to be the same, right? 'Cause it's the same thing. Again, I got several ways of doing this. Maybe I just took the 48, this 48 here, the row total, minus that 23.04. And lastly, here for the last one, here I got many ways to find this last one, right? I could take the 52, either with take the 52 minus this 52 minus this 24.96, this 52 minus that 24.96, or I could do it row and column totals. So it's either going to be 52 minus 24.96, or row total times column total, which are both 52 here, divided by 100. And that is 27.04. Okay, so there's our table. So now we have the observed values and the expected values. So once we have those, if we scroll back up, now we can get our chi-star, right? Because chi-star, you take the observed minus the expected, square that quantity, divide by the expected, and add all those up. So here you're going to add up the 4 cells. And then we can look that value up in the chi-square table with degrees of freedom. And here degrees of freedom is easy, right? Because degrees of freedom, this problem, so degrees of freedom here, well, how many rows and columns do I have? Well, I have 2 of each, right? 2 rows and 2 columns. Come on. There we go. So I have 2 minus 1 times 2 minus 1. Remember, these are original rows and columns. You don't count the totals. So the degree of freedom is only 1. Well, that should make sense, because once we find this first expected value, here is 20.04, we could find the rest by subtraction. So that's our degrees of freedom. And now what we need to do is to get our chi star, and I can probably stick in the bottom here, chi star equals, so take the observed value, the first cell, 26 minus the expected, which is 23.04. We square that and divide it by the expected, the 23.04. And now do that for the other three. So I take 22, the observed, minus the expected 24.96, divide it by 24.96. And actually there's two of those, right? So I've got symmetry here. So I've got another one of those. 22 minus 24.96 squared divided by 24.96. And lastly, we have 30 minus 27.04 squared divided by 27.04. So that's our chi star. Observed minus expected squared over expected, add those up. Okay, so what value is that? Okay, so that is, if you calculate those, about 0.380, the first one. The next two, which is the same thing, are about 0.351s. And the last one is about a 0.324. So very similar, all values very similar, which gives us a chi star value of 1.406. Okay, so that's our chi star value, 1.406. So our p-value is the chance the chi-square value in the table is bigger than that, right? Or greater than equal to that. Okay, so what we need to do is we need to go to the chi-square table and see where does this value fall with our 1 degree of freedom. Right, we want this value, 1.4 and 1 degree of freedom. So bring up the table. So let's try and get the table here. So here's our the chi-square table. So here we want 1 degree of freedom, right? So right here, 1 degree of freedom. And we're looking for 1.406, right? With 1 degree of freedom. Whoop. That's pretty ugly, but you get the idea. So notice here we go. It falls right here, 1.406. Falls between 0.1323 and 0.1642. So this is our p-value, falls between these two numbers. And remember, those two numbers, you have to switch the order. So our p-value is between 20 and 25%, between 0.2 and 0.25. So our p-value is between 0.2. Come on, put the point there. There we go. And 0.25. There we go. Well, what was that alpha? Well, if you don't remember, go back to the test. The alpha was 5%. And what I should do here, what I should have done earlier, so I'll put down here I was bad about it. We should put H0 and H8, right? I should write those down for the test. So here, H0, which I should have done at the beginning, but we'll put down here, was that the two variables, which are number of beers drunk and passing the test, are not related or have no relationship, right? And the alternative was that the two variables are related somehow. So number of beers drunk and passing the test are related somehow. And we said alpha here was 5%. Come on. Let me draw, there we go. So since our p-value is bigger than alpha, right, our p-value is bigger than 20%, we only allowed up 5%, so obviously the p-value is bigger than alpha. So since the p-value is greater than alpha, we cannot conclude HA. And what is HA? So we cannot conclude that number of beers drunk and passing the test are related. We're not saying they're not related. Maybe they are, maybe they're not. This is still a no conclusion, right? We have no conclusion. Maybe they are, maybe they're not. We just couldn't prove it. We had between a 20 and 25% chance being wrong if we say they're related. We only allowed up to an alpha of 5% chance being wrong. Okay, so that's all we can do there. So if your p-value is bigger than alpha, you're done here. Just say, I can't conclude they're related. That's all I can say. If the p-value was less than alpha, then we can say how we think they're related. I think what I'll do this time, before we go to the next example, which you can kind of see down here, I'm just going to show you first how to do this in Minitab. In Minitab, if you go back up to the problem, all you need to do is plug the values into a table in Minitab. So if I go to Minitab here, our values are what? 26, 22, 22, and 30. I'm just going to put those in. Notice I have to start at cell number 1 here. It doesn't have to be C1, but I have to start at cell number 1 here, otherwise I won't do it. So then that was 26, 22, 22, and 30, right? Was the last value. Go to empty cell. Now all I do is I go to stat tables, chi-square two-way table, because I have the data in a table. So I'm going to click on that chi-square two-way table. Choose the two columns I have my data in, and let me move it over, make this a little bigger so we can see it. And right there's your answer. So here are observed values, here are the totals. Underneath the observed values, the expected values, which are the same ones we got. Below those, it says chi-square contributions are printed below expected counts. So these, the 0.38, 0.351, 0.351, 0.324, those are the observed minus expected square root of expected. So notice here's our chi-square, here's our chi-star value, the 1.406, 1 degree of freedom. Minitab can actually get the p-value. It doesn't need tables, it can actually calculate it. So we said it's between 20 and 25%. Minitab finds that it's actually 23.6%. So same conclusion we'd have, but here's the actual value. So guess what I can do? I can take that, let's copy that. Let's see if it'll let me do this. I'm not sure if it'll let me do this. I might have to scroll all the way up to let me do this. There, I got my scroll. Let's see if I can put it in here. There we go. So there, is Minitab's results. So put those in. Okay, so that's that example. Now let's do one more example, and again we'll use Minitab for the example. This one we won't do it by hand, we'll just let Minitab do it for us. So first let me scroll down a bit, so we might need some more space. And then here's the problem. So this problem says, as you know, one of the highlights or lowlights of the first year seminar is the first year is the portfolio, right? Each student creates a portfolio that is graded by 2 people. One who's in the same department as the first year seminar instructor, which isn't necessarily true these days, but was till a few years ago, but most time it is still someone in the department. And one who's another first seminar, teaching another first year seminar section, which is how it works. That's still the same. So here are the results from fall 2003. So these are the results I had. So we know the scores, 6 is excellent, 1 is poor, right? That's kind of the rating scale. And you sum the 2 scores from the two people scoring it, kind of get an overall score. Well, in fall 2003, here are the actual results. Here are the actual scores people gave. So it shows for first year seminar readers, only 1 reader for one particular portfolio gave a grade of 1, but 16 gave grades of 2. So that might be the same reader giving more than 1 grade of 2 different people, but we don't know that. We don't know who's giving those grades, but we just know the total. And we had 23 portfolios from first seminar readers getting 23s, 23 getting 6s, the best score. Departmental readers, we have 2 who gave 1s. 2 portfolios got 1s. 10 portfolios got 2s. We have 32 getting 6s up here. So first it says, just looking at this data, does there seem to be a difference between the way first year seminar and departmental readers grade? Does one seem harsher than the other? Does this make sense? Explain. Well, here we don't have enough room to explain. If you look at this, notice it seems like, except for that 2 down there, right? That one's a little bit oddball, but for the rest of them, it seems like that the department readers are more on the upper end scale, right? They've got the higher scores, more in the bigger groups, the 6, 5s, rather than the 2s and 3s. So it seems like departmental readers might be giving better grades. So departmental readers might be giving higher grades. Why might that make sense? Well, actually it might make sense because of content. So I don't have room to read, write all that down here. But part of the thing with the first seminar, the scoring of it is not just the writing itself, but also the content of the writing. And if it's something specific to that department, a departmental reader will know better whether the content is good content or not good content. So they might be giving higher scores because they've got good content. So that's why it might make sense that you might expect to see that. Next it says, do the appropriate chi-square test relationship. Note there's one thing you need to do to the data before doing the chi-square. What do the results tell you? Well, we need a couple things here. One thing I didn't put down here, which I should have, is alpha. Let's use alpha, the usual alpha if you want to try and publish something 5%. So we'll say 5% is alpha. The other thing is you really need all observed cell values to be 5 or higher to do with the chi-square. Actually, it's not quite true. What it really is you need the expected values the ones you calculate to be at least 5. But that's usually harder to figure out because you have to actually do it and then figure out if they're at least 5. So by practice, people just usually look at the observed and see, are all the observed at least 5? If they're not, then the chi-square doesn't really hold. We're not going into the details of it, but the chi-square is really like a normal squared, and it's to do with the sample size in the normal and those things with the central limit theorem. So central limit theorem is somewhere behind here, kind of, but we're not looking at it. It's very kind of low down. It's buried down there. So notice here we've got a problem with these first two. Both these aren't at least 5. So the way you do it is you collapse cells and you collapse rows and columns in the simplest way possible to make sure all of them have at least 5. So what you would do here in this case, so here's our first year seminar reader, here's our departmental reader. Rather than throwing these out, you don't want to throw them out, you want to keep them. You'd have to combine them. So I'd combine scores of 1 and 2 into one group. So my first group would be 1 or 2. So I'd take the 1 plus the 16 to give me 17. And then you put a line here so I can make sure I get these separated. And the 2 plus the 10 gives us 12. For a score of 3, we keep those the same. So those are 80 and 66. Score of 4, those are still 116 and 107. For 5, it's still 79 and 91. And for 6, it's 23 and 32. So that's the change I make. I have to get rid of one of my columns. Okay, so now what I can do is I can go ahead and put this data in Minitab. So let's go ahead and first make it a little smaller here. Make this a little smaller here. There we go. Make this a little smaller here. Okay, I can almost see it. There we go. Let's see if I can get it in here. There we go. Now I can see it. So, now I've got the values 17, then 80, 116, 79, 23. There we go. And over here I've got 12, 66, 107, 91, 32. And up here, if I wanted to, I could put these groups. You don't have to. So the first one is 1 or 2. This is 3. This is 4. This is score 5. This is score 6. But I don't have any place over here to put the first year seminar departmental readers. So I've got the data in. I can now do the chi-square. So let's do it and see exactly what we're doing. What is it? We'll do the test, then we'll see what H0 is, what HA is, and we'll get the conclusion. So let's go ahead and do the test. So we'll do stats tables, chi-square two-way table, and now we have all C1 through C5s. I'm selecting those. So it selects 1 or 2 through the 6. Click OK. Here are my results. Let's get them. And then, so I'm going to copy those. See if I can find where, there we go. Put those in. And then let's see what these are telling us. Okay. So there are our results. So if you look at it, here are our observed values. Here are the totals. Underneath the observed, the expected. Underneath the expected, those are the chi-star things, right, that we add up. If we add all those chi-star things up, that gets us our 4.81 with 4 degrees of freedom, which makes sense, right? So you got 1, 2, 3, 4, 5 columns, and we got 2 rows, right? So here, get this down here. There we go. So let's get my pen back here. Right, so here at degrees of freedom, which makes sense, you've got 5 minus 1, so I had to combine 2 of the columns, times 2 minus 1 is 4 degrees of freedom. So that makes sense. We're given the chi-star is, if you add all those up, the 4.810, you're given the p-value, which we know is the chance chi-square is less than that value. Oh, not less than, bigger than that value. Let's change that one, bigger than. So it's greater than equal to that value, the 4.810. And we get a p-value of 0.307. Let's just check that with our table. So let's go to our table. We want 4 degrees of freedom here, right? So here's 4 degrees of freedom. Notice, what about the value we're looking for? The value we're looking for was 4.810. Notice that's before the first value. So all we could say here, if we're using this table, is that the p-value is bigger than 25%. Right, so on this side of 25% somewhere. That's all we can say. But with Minitab, it gave us an actual value, 30.7%. Okay, so that's our thing. What's our H0, what's our HA? Well, our null hypothesis. Well, what are our two variables here? Well, our variables are the reader. We've got first seminal reader and departmental reader, and we've got score. So those are two variables. So H0 is a reader, and score are not related, or have no relationship. Our alternative is that reader and score are related. Because if they're related, that means first seminal reader and the departmental reader are scoring differently. Right, so that would be that the readers are different. So this is the same thing as the readers score differently. But here, what about p-value? P-value is way too big. So here, since the p-value is bigger than alpha, right? The p-value is over 30%. Alpha, we said, was 5%, right? Because alpha is only 5%. So we cannot conclude HA, that reader and score are related. So we can't say there's a difference in reader. So slow down a little further. So we cannot say the readers score differently. Let's get a bit differently there. The problem here is, even though visually, if we go back up, even though visually it looked like there was a difference in the scoring, right? Looked like that the department readers gave higher scores. The problem here is the chi-square test is just looking for any difference. It's not looking for a particular difference. If we designed a test just to check whether departmental readers score higher, we may have been able to conclude that was true. But here, chi-square doesn't know what it's looking for. It doesn't know where the differences are. It doesn't know there's a pattern here. So it is just looking for a whole variety of differences. So it's not very powerful. So if you know what difference you're looking for, the chi-square test is actually a very bad test to use. It's not very powerful. It won't find differences. It's because it's looking for any possible difference. But if you know what difference you think there should be before you take the data, here we're kind of cheating. We're looking at the data after we've got it. But if you know before you take the data what difference you might want to look for, you might want to do something other than the chi-square if there's a particular difference you're looking for, because you can do a more powerful test that can might be able to get that difference. Okay, so that does it for the chi-square, so we'll stop here.